Okay, so let's continue. We have been moving along with neural models. So we talked about sequence representation and structured prediction. And we also talked about structured representation. Now let's look at sequence-to-sequence models. So we are here in the global map. So from this week onwards, we have 4 more lectures to go. And today, for sequence-to-sequence modeling, we're going to discuss 4 things. The first is a sequence-to-sequence model using recurrent neural network. So this is a very classical model, which were the first neural model that outperformed the statistical model for machine translation, and which caused a lot of interest in the research community. Then we talk about transformer, which is a self-attention network alternative to LSTM. Then we will talk about a new way of pre-training called contextualized word embedding. So you can understand that as pre-training more things than just word embeddings. Finally, we will discuss some ideas about transfer learning using neural network. Okay, so let's look at sequence-to-sequence modeling. There's a term which was very popular in the 2015 to 2016 area period, which is called end-to-end learning. Okay, and what do I mean by end-to-end learning? So traditionally, NLP used to be done using a long pipeline. So for example, if you want to do Chinese parsing, you have to do word segmentation before you do part of speech tagging and before you do constituent parsing, etc. So this is a long pipeline where errors in the previous steps can go to the next steps, leading to error propagation. Right? So it turns out that when you do neural modeling, you can use a single model where the input side is a Chinese sentence, okay, not segmented. The output side is just a parse, where the segmentation and part of speech are included. So this is called end-to-end learning, from one end to another, without the worry about intermediate steps. Why can we do that? It's because neural models are very powerful. Right? They can learn, as we've seen in the past few weeks, very complex structures implicitly in those neural parameters. So for machine translation, traditionally, you also need a very complicated pipeline. You need some translation model, a language model component. In the translation model, you need word alignment, which tells you which words translate to which other words, and phrase extraction, which tells you which phrase translates to which other phrases. And also this order relationship modeling. The Chinese word order is different from the English word order in terms of noun phrase modifiers, for example. If you think about Japanese, it's again different because it's not even subject, verb, object order. So, and then you need to discuss decoding, which is when you have a lot of probabilities, how do you multiply them together and find the most useful translation. But when you use a neural model, it turns out that you can do end-to-end modeling. What do I mean? English in, Chinese out. Right? Chinese in, Japanese out. And in the middle is just a humongous neural network, which is less interpretable. But anyway, we will talk about these end-to-end structures for sequence-to-sequence modeling. Machine translation is a sequence-to-sequence problem, but there are other problems. For example, dialogue generation is another sequence-to-sequence problem. No matter how many rounds of dialogue interaction you have gone through, right? So you can take the whole history as one sequence, and then the next utterance the machine is going to generate to the user is the output sequence. Okay, so dialogue modeling is a sequence-to-sequence problem. Another problem is summarization. When you have one or a lot of news documents, right? You want to give a digest to the user, so you put all these inputs as one sequence, and then the model is going to generate a summary to you. Okay, so a neural network for sequence-to-sequence modeling typically looks like this. It has an encoder component which finds a representation of the input sequence. And we have learned sequence encoding, so this is familiar. It also has a decoder neural network, which you've never seen yet, so which generates a sequence. Okay, so for machine translation, it's like source language in, target language out. And for dialogue, it's like all the previous utterances, many rounds of utterances in, and the next utterance is the output. So people looked at sequence-to-sequence models back in 2014, or even earlier. And one of the representative model is a recurrent neural network model. So you have an encoder, okay, which could be a LSTM sequence encoder. And you have a decoder, which is another LSTM. But this LSTM generates the target sentence token by token, which we call an autoregressive generation model. Okay, token by token generation is called autoregressive generation. So encoder, we can just use bidirectional LSTM, which is nothing surprising, and you can stack multiple layers of bi-LSTMs, just as what we did for classification and structured prediction. And when we have this, we want to compress the whole input sequence into one vector. Now, how can we do that? Of course, we can use the last hidden state from the left to right component and from the right to left component. When concatenated together, it's one vector for the whole sequence. Or we can do sum pooling over all the hidden states, as you've seen before. But this is an aggregation. And next, the decoder is what we have not seen. So suppose that you have compressed the whole input into one vector. Now what you want to do is to generate a sequence, generate a sentence. Okay. How do you generate a sentence? As I said, autoregressive generation will predict one token after another. Okay. And this can be modeled by a state transition process, just like an RNN. Now you're given the pseudo beginning of a sentence, right? Bracket S, all right? And you recurrently feed the previous word into a state machine, okay? The state machine also has an initial state. And it regressively, okay, takes the previous state, the previous predicted word as the input, and generates a next state and the next word. Okay? So this is a recurrent process. And what is the initial state? As I said, we have compressed the whole input sequence into one vector. So this vector is the initial state, right? And then we take this initial state and take the embedding of the beginning of the sentence, and we feed that to an LSTM step, okay? And we get a first step, time step hidden state. Using this hidden state, we feed that to an MLP, a two-layer perceptron, softmax prediction of the next word. So this part we are familiar, right? So this part is the same as the neural n-gram language model. We have a hidden state, and I want to predict the next word. It's a two-layer perceptron. All right? And then for the next steps, we just follow the recurrent step when we have the previous predicted word, yi minus 1. Okay, in general, we just feed that as the input and feed the previous hidden state as the state, and we obtain the next state, and we use a MLP to predict the next word. So we repeat this step until the end, okay? So what do I mean by the end? Maybe we have a special token /s, right? So whenever this is predicted, we stop the process. And this algorithm is called a greedy local search algorithm, right? Because every step we just predict the most probable one locally. And we go from the beginning to the end. So how do we train the model? Okay. When we train the model, we don't have to decode the sentence from the beginning to the end. We can use some technology called force decoding or teacher forcing. And the idea is, okay, when you do autoregressive prediction, generation, you need to feed the previous word, okay, into the LSTM to predict the current word, right? So in the decoding process, you just predict one word and use that word as the next input. But when you do teacher forcing, you just place the gold standard output sequence as the previous word sequence into the model. As I show you here, the green part in this picture, okay, shows you just lay out all these Y tokens from S until the last token, right? And of course, you feed the X tokens, the source tokens, in the encoder. And then the encoder and decoder can do the hidden state computation, all right? And then you use the gold standard previous tokens and predict all the output tokens. And you have a loss. You have a cross entropy loss for multi-class classification at each time step or by predicting each token, and you accumulate all this cross entropy loss as the total loss for training your model, okay? So training can be done sequence by sequence in this way. So it's not token by token. All right. So you say, all right, teacher forcing makes training a little bit different from testing if you are sharp. Because during training, you always have the gold sequence, right, as your input. But during testing, you can make errors. And once you make an error, your model suddenly panic because the previous tokens are some sequences that have never seen or some distribution it has never seen in training data, Okay, how does it deal with that? How does it make training simulate the testing process? Okay, I refer you to the textbook. There's some technology called scheduled sampling. The basic idea is after you train the model for a few iterations, you can mimic the testing scenario by sampling your own model output as your training inputs. Okay. But this model doesn't really beat the best statistical model for machine translation. Okay, it's elegant, it's conceptually simple, but it doesn't work competitively. So this makes neural models under suspicion until someone found you could strengthen this sequence-to-sequence model. Okay, the weakest point here actually is the connection from the source to the target. You know, we compress the whole source sequence into one vector and feed that as the initial state for autoregressive generation. So this is a problem. When compressing something into one vector, you lose a lot of information. The machine translator cannot remember all the fine-grained details for the source sequence. Okay? So to solve this problem, so one idea is we could keep the whole source sequence hidden state at hand when you try to predict each target word. Now, how do we do that? The main idea, okay, is to sort of look at all the source words, all the source hidden states, okay, and find one that is the most relevant to the current target word, okay, and aggregate the whole source sequence into one vector by assigning weights to the most important ones, okay, before you generate the current target word, okay. So this is something we learn, right? So this is called attention. So when you predict every target word, you use the previous hidden state to look at the whole source sequence and do a weighted aggregation as a context, a source context. So this means when you predict each source word, you can do a different aggregation of the source sequence so that you find the most relevant and important source words. How do you do this aggregation? Okay, so actually you can do it before you calculate the current target hidden state. You can use the previous step hidden state here, okay? So which is H decoder I-1, the previous step hidden state. You use that as a query, okay? You use that as a query to query against all the encoder hidden states, H encoder 1 to n, okay? And you do a weighted sum of these encoder hidden states, as I show you in the first equation. And you can do all different kinds of attention scores, as I discussed with you a few weeks ago, right? There are 4 general attention methods. So you just pick one, okay, maybe additive attention, maybe dot product attention. Here we just used this MLP form, okay? So you use the previous decoder hidden state, concatenated with each of the encoder hidden states, and pass that through a 2-layer perceptron and calculate their score, okay? And then you accumulate the source hidden states into a context vector, I call it C, and you plug this C into the calculation of gates and hidden states, okay, in the standard LSTM equation. And all of you are very familiar with that, okay? So in addition to the current input X and the hidden state H, I added a C, you see? I added a C into these computations. But this C is not a peephole connection, okay? This C is the context vector. To avoid confusion from this C to the cell state C, I change the cell state C into C tilde, okay, in LSTM. All right, so this is very familiar, so I will not spend time on it. So I got a new way to calculate the target hidden states, right? And from this state, I do the same prediction for each target word by using a two-layer perceptron. And this model turns out to be much stronger than the naive sequence-to-sequence model, just because we added connection from the target to the source. And it was the first model which beats the traditional pipelined, very dedicatedly crafted phrase-based statistical models, okay? We can still do better. We can add beam search to replace greedy search. Okay, so when we predict each target word, you know, our equation was the probability of yi given x 1 to n and y 1 to I minus 1, okay? Or we could write that as y smaller than I, okay? So this is the probability. And you know, this is like a probability chain rule, right? When we accumulate this thing together from 1 to m, we get the probability sequence, right? So y 1 to I, for example, x1 to n, y, nothing, okay? Nothing. So this can be done by accumulating all these things, right? From 1 to I, right? So it's equal to the product of j equals to 1 to I p yj given x and y smaller than j. So we could do that accumulation. So in the end, it's this sequence probability which we're interested in, right? When we select the high-scored sequence. So, but greedy local search doesn't reflect that, right? So we can instead use a search algorithm, like beam search, to reflect this thing. Okay, it's also in the slide. It's a product. We want to find subsequences that find the maximum of this product. And this is an animation of the beam search process. So from the beginning of the sentence, we first predict the first word, and I'll suppose, okay, so this is a translation. I'm ignoring the source, just like when I ignore the words in explaining HMM. So maybe he and I are two of the most highest scored words. And then from both words, we can generate a lot of next words, okay? And we can multiply these probabilities together, right, to get the sequence probability. And we can still select the highest scored two for the next step, right? So next step, imagine that the highest scored are I like to and I like play, okay? And then we can further extend this to the next sequence to find the sequence probabilities. And maybe the high scored are I like to learn and I like to play with, all right? And then we further continue, we find, okay, I like to learn NLP is the highest scored, okay? Yeah, now suppose we're translating this sentence, okay? So, so this is beam search, you know. The locally most probable words may be not a part of the globally the most probable sequence. So beam search can avoid search errors. But when we do beam search, you know, we're not sure when to finish the sentence, because when we do greedy search, we know when we predict the end of sentence, we're done. So for beam search, we can wait until maybe all of the hypotheses are finished, which will take a long time, or maybe the most probable sequence is finished, or we can have a maximum cutoff step, okay, t, which is a hyperparameter. So whenever we generate to t words, even if it's not finished, we terminate. This is about finishing. And also, for beam search, every time step you need to rank a very long list, a list of, if the beam size is k, right? K times the vocabulary size, rank list, right? So this could be even time consuming. Maybe we can prune at every word. So for every word, we don't enumerate V, vocabulary size, candidate word, but we only enumerate maybe 2K most probable words. Okay. So this will reduce the time complexity. Pruning, all right? So I will leave you to read, okay, specifically how to prune this beam search process in the textbook. But if you're not doing it, you get the main idea, you're fine. Next, we are interested in some further functionalities. Like, it can be observed for a lot of sequence-to-sequence problems, we need to duplicate source spans in a target. For example, in machine translation, right? So there are names and there are like entities that needs to be copied from one language to another. This is a code mixed example. When we translate English to Chinese, maybe the abbreviation NLP can be placed there rather than being translated. Okay. So similarly for other sequence-to-sequence problems, we have the same need. When we do dialogue, for example, you need to copy some of the history mentions to the next utterance. Okay, so when you do this copy, sometimes you don't want to regenerate the sequence to make sure that the copying is correct. For machine translation, you even want to do the copy because the target vocabulary is different from the source vocabulary, right? So if you generate, you can never generate NLP if the vocabulary has only Chinese characters. So you need to think about how to copy. So how do we formulate copying? So the first thing is, for copying, you need to extend the vocabulary, okay? So if it's multilingual. When your target vocabulary is V, your source vocabulary is U, wait, it's not the source vocabulary. You don't need to integrate the whole English vocabulary into the Chinese vocabulary when you do translation. Why? Because you're only interested in the source sequence, right? So you only need to extend your target vocabulary with tokens in the source sequence. All right. So the union of all the source tokens is called U. And I add that to V when you generate the words, okay? So which is not a lot, okay, when compared to adding a whole vocabulary. The first thing is solved. The second thing is, okay, you have a new vocabulary. But how can you calculate a distribution over the new vocabulary, right? It's no longer a softmax distribution. Well, it can be a softmax distribution, but the calculation of the scores can be cleverly done. If you just think about it, when generate a new target word, it's a distribution from the target vocabulary. But when copying from a source, okay, you don't have to generate. You can look at the source sequence. Who can be copied? Okay, so how can you model that? All right, and how can you union the two scores into one distribution? There are two methods that are worth discussing. So one is called the pointer network. The other is called the copying network. And both use the idea of looking at the source, okay, when you generate the source tokens. But the pointer network, okay, simply reuses the target to source attention, right? When you do the sequence to sequence model. You know, when you generate each target word, you use the previous hidden state to look at the source sequence and you got a set of attention scores alpha. Okay? And the pointer network just simply takes this alpha sequence as a source distribution and takes the target prediction distribution as the target distribution. You have two distributions, all right? So these two, of course, don't add up to 1 because it's not a distribution over the union. And then what do? It takes some strategy similar to interpolation, right? Back in week 3, we learned interpolation, right? So you have two distributions, you want to union that into 1. Okay, you add a lambda to the first distribution and add a 1 minus lambda into the second distribution, and you get a 1 distribution. Now, how do you control these lambda values? You can treat that as a hyperparameter, or you can just train the single value when you optimize the parameters. The copying network, okay, says, no. We don't need to just look at the alpha values, right, in target to source attention. Why don't we recalculate these scores? Okay? How do you recalculate the scores? Well, I could use the current target hidden state, or I could still use the previous target hidden state, okay? And I recalculate a score, an affinity score to the source sequence, just like an attention function, all right? But this is a separate set of parameters, a separate set of scores, all right? So when you have these scores, and you have these unnormalized target vocabulary scores, you can put them together, okay? U here, V here, it's a single extended vocabulary, and you can use a big softmax to normalize everything, okay, into one distribution. So this is more elegant. What is this big softmax? You know, the unnormalized scores over the source is one part. The unnormalized score over the target is another part. You take the exponential of everything, add them together, is the partition function, right? Z. And you use 1 over Z to multiply with e to the power each score. Okay? So that is simply adding a big softmax function. That's it. That's for copying from the source. So that's almost everything about an LSTM sequence-to-sequence model. But there is one thing we didn't discuss, which is out-of-vocabulary words. Okay, you said, we're so familiar with OOV words. You already told me 2 methods to do that, right? Oh, I told you 3 methods to do that. The first method is similar to n-gram language models. You have a special UNK token, right? Added to your target vocabulary. And I said that doesn't help because it doesn't help you to guess unknown words when you do understanding. But this time it's even worse because when you do generation, okay, this whole thing is in your target vocabulary. Sometimes during testing, you will generate UNK because it's a part of your vocabulary. It can have the highest score, right? When you generate UNK, the reader doesn't want to read it, okay? I really like to learn UNK, okay? So what does it mean? You don't want to generate it. Then you say, that's easy. When you do the prediction, I just suppress, okay, the generation of UNK tokens, right? I remove it from the distribution. But that also causes inconsistency between your training and testing. When you train your model, you have a lot of UNKs maybe. And your next token prediction depends on this UNK. And now suddenly UNKs are gone. Okay, the model will degrade accuracy. So how can you solve the problem? You say, okay, you already told me several strategies. One is character-based word representation, right? So when you do understanding, you can just split the word into characters. And you can use a character CNN, right? And pooling, concatenate with the word embedding, and you get a new vector. For decoding, however, how can you do character-based decoding? All right. You don't know the character sequence yet, right? So you have to generate the target sequence character by character. So you no longer have words. Everything is a character. You generate I like NLP by generating I space LIKE space NLP. That's also possible. But that makes your target sequence very long. Okay, it leads to error propagation and reduced accuracy. All right. So I also told you one method called n-gram, right? N-gram-based word embedding. So when you do understanding, you take n-grams from the words and you embed each of them. Okay, when you add them together, it's a word representation. When you do generation, you can take similar thoughts. Okay, how about I generate a sentence by generating n-grams, subwords. Okay, but when you do these subwords, it's not so intuitive if you just generate the n-grams because they don't make sense. They don't always make sense. Okay, ideally, you need to break the words into morphemes and then generate these morphemes. Okay, it's more reasonable. However, for many languages, you cannot do the morphological segmentation accurately. So we have to turn to some statistical methods, okay, to find subwords. So here I want to introduce a method called BPE, called byte pair encoding. Okay, so this algorithm was originally designed to compress texts, not to segment texts. But it can help us to find statistical probability distributions to better compress, better segment words. Why is it called byte pair encoding? Because it compresses a sentence by repeatedly replacing the most frequent byte pair into an unused byte. Okay. I guess many of you learn algorithms. And many of you are not unfamiliar with this kind of thinking when you do text compression. Right? I just use one example. Now suppose the sequence is AAB. The sequence is like the sequence like that. Okay? If the sequence is like that, the most frequent byte pair is AA. Okay? Now suppose Z is not in your text. Okay? Now you can replace AA with Z, resulting in a shorter sequence, like what I show you here. Okay, then you repeatedly do the same. Now ZB is the most frequent, and you replace GB with another unused byte, okay? And you get an even shorter sequence. This is a loose-least compression algorithm. And you can go back and recover the original sequence. So how can you segment words or find the subword vocabulary using BPE? Now I just use a small corpus to illustrate. Suppose the corpus is as simple as 2 bad, 2 better, 3 east, and 4 west. Okay? These words. So how can you find subwords from this corpus? You can initialize your vocabulary by using all the characters. Okay? And they are shown on the right. Start with all the characters. And then you start running the BPE algorithm. The most frequent pair of words are S and T, a pair of characters. Oh, now you don't find characters, but you find subword pairs, okay, which are essentially character pairs, okay. So because the initial subword vocabulary only contains characters, so you found S and T, you add ST into the subword vocabulary. And you can repeat this step, okay. Now, because your subword vocabulary has a new item, ST, you treat ST as another byte, okay, when you calculate frequencies. And now the next most frequent is BE, you know. If it is something XST, it's also okay, you know. So because the next most frequent is BE, you add BE to the subtoken vocabulary. And you repeat until maybe your subword vocabulary reaches a certain size. You stop there, okay? You set the size. You want your vocabulary to contain 10,000 words, you set 10,000, okay? You want it to contain 20,000, you set 20,000. But whenever your vocabulary size already reaches the limit, you can stop it. Now, when you get the vocabulary, you can use the vocabulary to segment any new word, all right? Now, suppose you're trying to segment best, you know. How do you do that? Okay, you just match the longest subtoken to the vocabulary. Now, if best is in the vocabulary, then best is one subtoken, is one token. Of course, in our case, best is not in the vocabulary. Then what do? You first match the longest subspan, BE. You found it. And then the next subspan, you continue matching, you found ST, and you're done. Okay, so best is chunked into BE and ST. One token into 2. Now, how can you do loosely segmentation? So we have to remember that there is a chunking operation in between, right? So you can add some special symbols like at after BE or before ST, no matter what you do, right? Or add # after BE. Okay, so when you recover the thing, you can take this as a clue. Now let's look at transformer. So transformer is a SAN alternative to RNN sequence-to-sequence model. Okay, and it's a highly engineered SAN, which is a more complicated SAN compared to week 9. Okay, so, and also it has an encoder and a decoder. So the encoder is a extended SAN. The decoder is another SAN, one that does autoregressive generation. Okay, so the probability it calculates is like that. All right, so let's look at the model architecture first. Overall, it's like this. You will see different versions of this over the internet. It has an encoder with KE layers. It has a decoder with KD layers, and basically like that. Okay. So the input sequence is fed to the encoder. So as the standard SAN, you need to do position encoding. Okay. Otherwise, you lose the sequence structure information. So you first use the embedding lookup layer to map every input token into an embedding, and then you use hard-coded position encoding, okay, a P vector. The even bits in P are the sign functions, are the odd bits are the using the cosine functions. Okay, so it's hard-coded V vector. And you add the word embedding with this position encoding vectors as X hat. Okay, so in the end, you get an X hat sequence. So this is the input. Okay, the source sequence is fed to an encoder structure, just like LSTM. Okay, but this time it's an SAN encoder. So it has many layers. Okay, many layers of SAN, and then you get an encoder vector sequence called H encoder. I will discuss the encoder structure later, okay? But this H encoder is then connected to the decoder. All right. So the decoder, okay? So the decoder is autoregressive generation. What do I mean? It means that you're given the previous y smaller than I, right? And then you sort of, you use that as your input to predict the current yi, the next word. When you predict the current yi, you take yi minus 1, you know, the previous word, as the input, and feed that through many, many layers. But before you feed the previous yi minus 1 into many, many layers, you have to encode this into a target vocabulary embedding, right? And you need to add position encoding to it also. So in other words, so the generation part also needs position embedding, okay? And after the position embedding, you know, you feed this previous word y hat I minus 1 into many, many decoder layers. You get a representation called H decoder I, okay? You use H decoder I as the input through a multi-layer perceptron, this time a single layer perceptron, to predict the yi. Okay? So this is the big story. After the big story, we have to look at, okay, inside the encoder, right? So, you know, there are many, many layers of encoders. You know, each layer is a self-attention network layer. But as I said, it's more complicated than self-attention. How much more complicated? Let's first look at, okay, the first equation is the encoder. Now, the next few equations are the encoder layers. You know, the encoder zeros layer input are the X hat, you know. And then for every encoder layer, you take the I minus 1th layer as input, you feed that to a self-attention network, you get the ith layer hidden. You stack these layer structures for KE tiers, and you got the last tier is the H encoder output. Okay? You zoom in a little bit, right? And now let's further zoom in. So for each encoder layer, what do? For each encoder layer, it's not as simple as SAN, but it has two components. One is a complicated SAN called multi-head self-attention. And the next sublayer is familiar, it's a feed-forward layer. In other words, okay, so when we learned SAN, we already said SAN lacks nonlinearity. And how did we solve that? We solved that by using QKV mapping, right? And this time, it's more explicit. So in addition to QKV mapping, you add a feed-forward layer. Equations are like this. For multi-head attention layer, there are two things, okay? One is a MHA function, multi-head attention function. You haven't learned it yet. The second is a layer normalization function. You have learned it. But in layer normalization, inside the bracket, there is an addition. What is this? You don't directly take the MHA output to be layer normalized, but you add this MHA output with the HE input. Okay? So it's a shortcut connection which you have already learned. Right? So it's also shown in the picture. You have a separate wire, right? Before you feed this H in to MHA, okay, you have a separate wire which does the shortcut. You add that to the MHA output, okay, before layer normalization. So this is the multi-head attention sublayer. The second sublayer is called feed-forward sublayer. As you see, there are also two equations here. The first is FFN, where each hidden state, the hidden state for each input token goes through an MLP. Nothing surprising. Second is a layer normalization, but again, okay, there is a shortcut connection. You don't directly feed the FFN output to be layer normalized, but you add the FFN input to the output to be layer normalized. And in the picture on the right, you will see that there's a wire, okay? There's a like a sideway, right? Sideway from the input directly to the layer normalization. Okay, so these four equations describes the encoder layer. Each layer is like that. So when you compare with our self-attention network, you will see that three more equations are done, right? Layer norm, FFN layer norm, these are three extensions. But even the attention function is MHA, no longer QKV attention. So what is that? Let's first recap the QKV attention. You know, okay? So what is attention QKV? You use, okay, every token as the query to query every other token to aggregate them, okay? But before you do that, you map every token into three representations, Q, K, and V, by using three projection matrices to do that. I call them W query, W key, and W value, all right? So in the end, the QKV attention is written in the second last equation. So you use these three projection maps to map the whole sequence, you know, which means each word is mapped using the same matrix, right? And then to calculate the results. I'm using Q, K, and V, okay, the three sequences to represent the mapped result. And in the end, you know, it's an aggregation of the value vectors by using query and the key attention. So if we use scaled dot product attention, okay, so the whole computation can be condensedly written as this simple equation. So V times softmax K transpose Q. All right. What does K transpose Q contain? Each element in this matrix Ij, okay, K transpose Q Ij, represents the ith row is a K, is a key vector, right? The jth column is a query vector, all right? So each column represents what? The queries dot product scores with every key, right? Each column is using one query to score each key, so result in each column. So this softmax function, by default, because we're all column vectors, right? So this softmax function normalizes each column in this resulting score matrix S. So in the end, each column is a distribution of the key vectors according to each query, right? Column J is the distribution of the key vectors according to the jth query. And V, okay, multiplied by that is the weighted sum of all these values which are column vectors, right? So that's why we can use this simple equation to describe the complicated scale dot product attention. All right, this is what we learned. This is nothing new to you. Only this abbreviation is new to you. Why do I talk about that? Because later I will use that. What is multi-head attention then? It is simple. It is simple. It's because one attention function doesn't really extract complicated feature maps. If you read my textbook, you will see one section in the attention section comparing attention functions with gates. You will find that they are very similar. But gates controls every element separately. Attention does not. So if attention is not expressive enough, then why don't we do many attentions? This is called multi-head attention. We have the same, okay, hidden vectors. But suppose we have a lot of different sets of projection maps, okay, to map them into a lot of different QKV values, right? So basically, you duplicate or you multiplicate this W query, W key, and W value matrices into multiple versions, okay? So in each version, you create a QKV attention. They're all separate, okay? And if you sort of reduce the dimensionality of the V vectors, you can get multiple versions of projections. Each reduces the dimensionality of the original input vector, okay? All right, so when you finish these multiple versions or the number of heads, okay, versions of attention, you get multiple versions of attention results, okay? And they contain rich features from different perspectives. You just need to concatenate them together. Okay, this is nothing surprising, right? When we have different feature extractors, we concatenate the results to get a longer feature. And you apply a matrix to that, okay, to achieve some feature integration. So in the end, you have W times the concatenation of every head. And every head is a separate attention function. So this is called multi-head attention. After, okay, you achieve this multi-head attention, you feed the result to the layer normalizer. and you feed the original input as a shortcut connection to the layer normalizer. And you're done. And after that, you feed the result to a 2-layer perceptron. I just write the equation out. You will see the first perceptron is a ReLU activated neuron, right? Okay, but pay attention that this ReLU is activated on every vector in the vector sequence, you know. Your encoder encodes a sequence of vectors, but ReLU applies to each vector. No interaction, right? And then the second MLP layer is just a no activation function layer. And after that, you do the layer normalization. Again, a shortcut, and layer norm is done on each vector separately. So this is the encoder, okay? And then let's go on to the decoder. As I said, the decoder is an autoregressive one. You just take the previous output word as the input, and you go through many decoder layers. The decoder function is like that, okay? You get HI decoder by feeding the encoder sequence as input and all these previous words as input. And then you can predict YI using H decoder I by adding a single layer perceptron. The input is YI minus 1 hat with position encoding. And the decoder consists of KD layers. Y hat I minus 1 is the input layer, H decoder 0. Okay. I have a next index I because I'm predicting the ith word. And then it's fed to a decoder layer. Okay, each layer does the same thing. You stack multiple layers, and the final layer is taken as HI decoder. And then you use HI decoder as input to one neuron, softmax neuron, to predict the output. Okay, so this is the whole story. Now, each decoder layer has 3 sublayers, not 2. So one is called multi-head self-attention layer. It's a MHA layer within the decoder. I need to look at my previous words. The second layer is a multi-head cross-attention layer. Okay, this is a target to source attention layer. I need to look at all the source words. The last layer is a feed-forward layer. Okay, each with layer norm. The equations are here. There are 6 equations. Multi-head self-attention is QKV. Using HI, okay, the current hidden as the query, okay, to query all the previous layer hiddens from the first word until the current word, okay? And then there's a layer norm with shortcut connection, similar to the encoder. The next sublayer is a cross-attention layer. Again, I use the current hidden as a query to query the source sequence, okay, H encoder, to get a new hidden. And then I feed that to a layer norm with shortcut connection. Finally, after self-attention, cross-attention, I feed that to a feed-forward network with layer normalization and shortcut connection. So let's look at them one by one. As I said, okay, self-attention uses my input hidden as the query, right? To query all my context, all the previous words, I minus 1, Y smaller than I, okay, to get my current layer hidden. So this is QKV attention. So I denote the previous layer, previous sublayer, hidden as H-in, right? So after this query function, I got HDECCA, so cross attention, I. So it's a new hidden. After I get HDECCA, I add H-in, to HDECCA as a shortcut, and I feed that to layer normalization. I got HDECCA ln, if you're interested in these equations. And then with HDECCA ln, I further use that as a query to query all the H encoder, the encoder hiddens. Okay? The blue one is the one. Okay, the blue one, layer normalized is the one to query all the green ones, and I got an orange one. Okay. And this orange one is called HDEC. The previous one is self-attention, so DECSA. The new one is cross-attention, DECCA. And then I feed that to a layer normalization, okay? And feed-forward is exactly the same as the encoder. As a two-layer perceptron with ReLU in between. And then I feed that to the layer normalizer, and then the output layer. Okay, that's it, right? I just do encoder, extended self attention network, decoder, token by token self attention network, okay? With 3 sublayers. We're done. Auto-regressive decoding. Training is the same as LSTM model. I do force decoding. When I have the gold standard training examples, I put X and Y, the gold sequence X, gold sequence Y, as input to the encoder and decoder. Okay? And then I use the transformer to calculate the output distributions on each token, and I take the cross entropy loss. The cross entropy loss for objective. I can do the training. But there's one thing to notice. When you do the teacher forcing, okay, then your decoder tokens can be computed together. This is the design trick of transformer. What do I mean? Originally, when you do the auto-regressive decoding, you calculate the hidden for each output token, right? 1 token, 2 tokens, 3 tokens, just like LSTM. But when you put all these gold sequence as input, then your decoder transformer will be similar to your encoder transformer because you have a sequence. You feed the sequence to an SAN. So each layer can be computed simultaneously. And this is the new equation. You take y1 to m as your input, okay? Similar to x1 to n, right? And you feed that to the first decoder layer self-attention, next decoder layer cross-attention, next decoder layer FFN, repeat for kd times, you get the token probabilities, right? And you can calculate loss. This is layer by layer. And I write the decoder just as I write the encoder using the capital letter for vector sequences, right? And you see it like this. but it's not exactly the same as the encoder. Let me see who is the fastest. What's the difference? Cross-attention is not mentioned. In this equation, what is different from the encoder? Is it exactly the same as the encoder? Except for cross-attention? There's one difference. It's here. Is it a typo? No, it's not a typo. So MHA, multi-head attention, is the encoder, right? Why do I change it to MHMA? What is MHMA? Because each decoder token can see only the previous tokens. It cannot see the future tokens. In the encoder, everything can see everything else. But for decoding, okay, the attention can be done simultaneously, but every token can only look at the previous tokens. If you allow it to look at the next tokens, there will be a bug, right? So MHMA is used to describe this phenomenon. It's called multi-head mask attention, okay? So basically, you can think about you have a mask map, okay? So each a row represents a query. Each column represents a key, in this equation. So you can do attention only when the query is greater or equal than the key, okay? Not do the query otherwise. So how can you easily represent that? I can represent that using a matrix M, okay? When I is smaller than J, I just set M value to minus infinity, okay? So in this case, if I add these M values to the K transpose Q values, I just set those exponential terms to zeros. Okay? And you look at the equation, originally it's K transpose Q, right? And then you add some minus infinities to those that cannot be reached. So e to the power of those are removed. In this way, your attention is right to left. Okay, masked attention. So that's all. So transformer is like this. So you can have different numbers of layers for the encoder and decoder. And normally the number of layers are all greater or equal to 6. For LLMs, okay, which we will see 2 weeks later, the number of layers can go to over 100. Okay. So what determines the size of your model? The hidden size also decides your size of the model, right? The number of attention heads decides the model size. The number of layers decides the model size because each layer uses different model parameters. All right, so the model can go big. The hidden size can go to 10,000 also. When transformer is big, training is difficult. It turns out that random initialization will lead to unstable training. So I have to tell you one more trick in addition to the tricks in week 9. It's called warm-up. What is warm-up? Okay. We learned a learning rate decay already, right? So when you do SGD, when you go deep into the iterations, you want to reduce the learning rate. Why? Because you want to find the valley, right? So when you try to warm up a model, you do the opposite. the model is very unstable if you use a initial learning rate. So you cut the learning rate to maybe 1/10 of the initial learning rate, and you train a model for a few iterations, okay? When the model goes a little bit in shape, and you start the normal training. So this is called warm-up training. So you can do warm-up training by controlling the learning rate or by controlling the data or some other tricks. But typically you control the learning rate. And then you gradually increase the learning rate to the original initial learning rate, okay? By using linear increasing or exponential increasing or whatever. So your learning rate of the model will go something like you go up and then you go down. This is called the warm-up, okay? So this is called learning rate decay when you train a model. But of course, you can also warm up a model using a small set of data. When you have a lot of data to train an LLM, for example, it's unstable in the beginning. But when you use a small set of data, the model can fit it very well. You can also reduce the data. Or you can, for the first few training iterations, you can manipulate the input feature map. You can normalize the feature distribution for a few iterations without changing the learning rate whatsoever. You can use some tricks, okay, before you train the model, okay, to find a stable start. So this is called warm-up. Okay, that's all. And so far you can train the transformer. But the advantage of transformer are at least twofold. So let's look at the first thing, which is the training speed. As you know, when you train a model, you use teacher forcing, and your decoder can be done just as the encoder, right? So it's very fast. The computation doesn't scale with the input size. But for LSTM, you cannot do that. For LSTM, the training is in the order of n. N is the target size. Okay? So, when you have a GPU, you do the computation in parallel. Transformer does training of a sequence in O1 time. But LSTM has to do it with linear complexity. This is one advantage. The second advantage is that LSTM, right, doesn't allow each decoder node to look at every other decode node directly. Okay, so it has to go through a path length of n to interact. But as a self-attention network allows each decoder node to look at each decoder node. So they interact better. There is a disadvantage, which is the computation complexity is larger because every node have to look at every other node. So this computation time is in the order of n squared. N nodes, each node look at n nodes, n squared. For RNN, it's easy. Each node look at one node, or ON. So computation for transformer is larger than RNN. All right. That's transformer, and that transformer has been used to build many models. And people found, for certain circumstances, the standard setup doesn't work. So they have to improve transformer. So there are a lot of variations to transformer. Okay. Too many variations. But I have to mention a few salient ones because you will face them. The first is activation function. You said we have been fed up with activation functions in week 9. But that's not all of it. Transformer uses ReLU. But you know ReLU has a problem. We already mentioned that in week 9, right? Week 8, even week 8. So which is it leaks information for negative inputs. It's all 0. And there are many, many alternatives to ReLU to fix this. For transformer training, people have found 2 alternatives that are close to the shape of ReLU but differentiable. So one is called the swish function. Okay, it's written in this equation. All right, it approximates ReLU, but not that closely. And then people found one other function that it's like a more accurate approximation. It's called Gaussian error linear unit. And the equation is written in the slide. Okay, it's complicated, but all you need to is to use it. So I will not explain it. Well, you can see in the picture that it's a more accurate approximation. That's not the end. You have to learn some other families of activation functions. They are called gated linear unit. Okay, we're familiar with gates. So some people even use gates in activation functions to improve the expressiveness of the FFNs in transformers. So the gated linear units are written in these equations. Okay. So basically, you use the same input, okay, to compute a gate vector and to compute a value vector, you know, very similar to LSTM. And then you use the bitwise product between the 2 to get the resulting vector. This is already like a neural layer. This is already a little bit more than the activation we learned in week 5, right? But this turns out to work very well. And then there are even improvements to this gated linear unit. Swish GLU. It replaces the simple sigmoid function to a more complicated swish function. And Gaussian error linear unit, which further replaces the swish function to the GELU function we see in this slide. And that's pretty much it. That covers almost every model you will see nowadays. Every popular model you will see nowadays. So this is activation. But people also thought about layer normalization. Can we improve that? Yes, you can. So, you know, I told you warm up, right? Warm up makes training more stable. But in the earlier days, people found that if you change the layer normalization a little bit, you can even remove warm up. And nowadays, when the model becomes even larger, this doesn't necessarily work, but empirically it still can give a stronger result in some models. So as you learned, a layer normalization is to remove covariance shift, you know, and that's to normalize your input vectors, right? So when you do layer normalization after you do MHA or FFN, you benefit your next layer, but you don't benefit yourself. So why don't you do layer normalization before you do MHA or FFN? Okay? So the new method is called the pre-layer normalization. And it's written in the picture. Okay? Maybe I don't have to write the equations to you. All right? And you just replace layer norm with the function itself. And more people have found, okay, we can also improve the layer normalization function. Originally, there is a scale, there's a bias, and you use the current vector minus the mean divided by the standard deviation as the normalized version. Okay, so you normalize a vector like this. But people have found that maybe you don't have to calculate the mean. Why don't you just use RMS as the normalizer? Root mean square. So basically you take the root mean square of every element in a vector. Okay? And you use that to divide this vector. And you multiply that with the scaling, the gain vector. Okay? And that's it. And people try that, it sometimes gives a stronger result compared to layer norm. All right. So we talked about activation and layer normalization. There are also attention. There are also the position encoding. They all have alternatives. So this attention alternative is actually an optimizer rather than something that changes the results. It's like this. When you do autoregressive decoding, you recursively use the current token as the query to query all the previous tokens, right? So each token will be used as a key and a value vector to serve the next one, the next one, until the last one. So every time you have to do the mapping function, okay, by multiplying this with a matrix. So that makes the computation redundant, okay? So you can use the simple thinking of caching. So the idea of caching is you have an array of previous keys, okay? So when it's empty, you calculate it. But when it has values, you just reuse the calculated version. So this is a very common trick in algorithms. Just cache things to avoid repeated computation. Equation-wise, it's like this. You have a key array, you have a V array to store existing values. And the animation is shown in this picture. I got it from the internet. So, okay, so this is KV cache. Now let's consider position encoding. Position encoding is also something that can be optimized, especially for longer sequences. Why? Think about it. You add a position integer to every word, right? I like NLP, all right? I is first, like second, NLP third. You add these position encodings to the three words, and then you train the model, you understand what is I like NLP. But then you got a second sentence. My instructor said, I like NLP, okay? Now I becomes 4, like becomes 5, NLP becomes 6. The embeddings are completely different from I like NLP, but they mean the same thing, okay? When I try to understand like, okay, I look at I on its left, NLP on its right. The relative positions are fixed, no matter where you shift the sequence, okay? The absolute position encoding doesn't allow you to model this. It overfits your data, okay? But when you have a lot of data, maybe this is not a problem. However, when the sequence size is long, you can shift I like NLP anywhere. The data scaling doesn't necessarily catch up with the position scaling. So you have to think about, can you do the relative position encoding? Okay? So, where do you feed these relative positions? We cannot feed them in the input, because this is about the interaction between a word and its context. It's all relative. There's no absolute position encodings that can do that. So we have to hack the attention function to add these relative positions inside. In other words, it's when I look at my neighbors, I look at, there's an I, okay, on my left. It's one word before me. It's when I do this, I integrate the relative position information. Okay, so how do I hack the attention function? So originally, it's absolute positions added to the input, okay? And when I substitute that into the QKB attention function, I got something like this. I got a lot of terms because you have an addition. It's x plus p. When you have addition, you expand your dot product scoring, you get these 4 terms. Why do I expand it? Because I need to show you where p is, right? Okay. So when you do relative position encoding, your x is not added to p. So it's x. And the attention function is still like this, but you need to calculate an S score between query I and key j, okay? And it's just take it as a f function with qi and kj and I minus j, the relative position, okay? I want a function here, okay, to replace a function here, this long function with 4 terms. How do I do that? There are different strategies. So first strategy is I just look at the original function here. There are 4 terms, okay? I want to replace the absolute position pi with a relative position called Ri minus j. And this Ri minus j is the first to put the number I minus j, which is an integer, right? I put this integer to the position encoding function. I got a number. I got a vector called Ri minus j. And I just use this Ri minus j, okay, to replace the pi and pj in some functions. And I got different ways to do position encoding. So the first way, as you see in this equation, is I just delete the pi and pj terms, okay? There are 4 terms in the original function. I delete 2 of them, and I replace the position in the second term with rij, and I got a function f. So this is a classic way of relative position encoding. I change the attention function. There's a second way, okay? It's called XLNet way. XLNet is an alternative to transformer for encoding longer sequences. So rather than deleting 2 terms, okay, it replaces a few terms with relative positions. I leave the detail to you to read the textbook, okay? But then some other people say, wait, in all these classical and XLNet functions, you have interaction between the positions and the word embeddings. They say we don't want that. I want to separately calculate a score on the relative position and a score on the word-word interaction. It's like word-word interaction is a dot product attention. Then I just add the relative position score to the dot product value. Can I do that? There is a position encoding method called alibi. I don't know if my pronunciation is correct. It adds basically a hyperparameter m, okay, times this I minus j value as the relative position score, okay? And I add a negativity to it. Why? Because the longer the separation, the weaker the influence, they say, okay? So this is a very simple replacement of the original function on the left. And then for some other models, okay, they say m can be trained. You don't need to specify that as a hyperparameter. I can train that. Then you end up with this new relative position called T5, or learned. I can call it learned relative position. Okay, so these are the 4 most common relative positions. No, actually these are 4 out of 5 most common relative position encodings. So all these methods, you know, you take the relative position as a vector and you add that to the computation of attention score. But there's one more method that changes the matrices, W, by integrating relative position information into the matrices, rather than taking the relative position as a vector, okay? And this kind of method is called the rope, rotational relative position encoding. So if you look at the equation first, okay? So this position encoding is integrated as different matrices and multiplied with these W matrices, right? Rather than taken as vectors to replace the P vectors. So this is a salient change. They are matrices. And how do I interpret matrices like this? Sine, cosine, sine, cosine, okay? It turns out that in high dimensional vector geometry, they represent rotation functions. When you multiply these matrices to original matrices, vectors, you rotate the vectors to a certain degree, okay? Why do we need rotation? It's like this. When the output sequence is very, very long, you know, learning absolute position difference will still cause overfitting, okay? You want some like periodical patterns in order to scale up. Just like your absolute position encoding have some sine, cosine functions for periodical patterns. So these rotation functions are periodical, at least, okay? So they allow your relative position encoding to scale to infinity. So that's the basic idea behind it. Okay, so we are in the position. Now, lastly, many people thought about how to simplify attention. As I mentioned earlier, you know, the computation for transformer is complicated, all right? So each word will look at every other word when you do the attention. This is n squared complexity. Can we simplify that? Right. I used the encoder as an example, which doesn't have the attention mask. But you can do the attention mask for the decoder, but by just deleting a lower triangle. Okay, so the first way to simplify attention is to say, okay, why don't we have local attention, which is every word can only look at an n-word window around it, okay, rather than everyone else. So this makes your word-word interaction weaker but makes your computation faster. Okay? Now other people say, no, I don't want to lose the accuracy. And I realize that the first few words are very important in the meaning of a sentence. So why don't we allow the first few words to interact with every other word? For the next words, I use local attention. Okay? So this is one attention pattern people use. So other people say, no, I still want to have some interaction between every word and everyone else, but I want to keep low computation cost. Then what I do? I randomly sample a constant size of words, okay? And I allow them to interact with each other. So this is like first few words global, other words local, but some words randomly global. Okay? So there are even other people who say, okay, we can have periodical attention function. Every word look at the local window, and maybe I jump 3 words, jump another 3 words to look at. Okay, all these kind of attention simplifications to reduce the complexity from n squared to linear or log or whatsoever. Okay? Many people study that. Okay, that's all. That's all the alternative. You can see that from the bottom, which is the position encoding, to attention, to layer normalization, to activation, people have thought about every possible way to improve transformer. Now, let's move on a little bit. Let's look at some new thinkings on language modeling and pre-training. You know, pre-training is closely related to language modeling. And we learned n-gram language models. And the neural version led to word embeddings. Okay? But n-gram language models are limited in the context range in the sense that every word only looks like at the n-1 history. Now, people have wanted to build a language model where every word can look at every other word in the history. But for traditional models such as week 3, we could not do that because it would be too sparse. The model will be too big, right? Even 6-gram language models were infeasible. But for neural models, we can do that. The idea is very simple. We just take the RNN decoder out. That's a language model. Okay? When we don't have an encoder, when we do the decoder only thing, we have a language model. You start with the beginning of the sentence, okay? And the model parameter H0, not the encoder output. And then you just repeatedly do the same thing as your LSTM decoder. And you have a language model. I call that language model recurrent neural LM. Of course, you can stack multiple layers just like what you do for transformer or for the LSTM encoder decoder. Okay? And this language model turns out to be much more powerful than the n-gram language model. And people say, okay, can you pre-train this language model over the internet? And after you pre-train such a model, okay, you got a multi-layer RNN-LM. And you have many layers. Okay. Can we use this thing as pre-trained word embeddings rather than just taking every word as an embedding? But these are not word embeddings anymore. These are sentence embeddings. right? Because for every sentence, you put your RNLMs onto it, you get a set of different embeddings. Each word in different sentences will have different embeddings. Okay? So we can, okay, given any sentence, use my recurrent language model on it to get a lot of hidden states. Now let's suppose we have k layers, and we can add the embedding of this word on each RNLM layer together. We can calculate the weighted sum, okay? And that's the embedding of this word. In this context, we call it contextualized word embedding, okay? And you can actually do two RNLMs, one from left to right, one from left to right. If you concatenate in both directions, okay, you get a hidden representation of the full sequence. And this is called ELMO, okay? Embeddings from language modeling. These ELMO embeddings are context dependent. You have the same word, put it into different sentences, you get different embeddings of the word. Okay? How can you use ELMO? You remember in week 9 and week 10, we learned two neural network structures for classification and structured prediction, right? And both of them share the same structure, which has a sequence encoder. All right. Now when we have ELMO, we don't just put the word embeddings to the input. We can put the word embeddings both to the input and to the hidden states, like after the sequence encoder. So this is what we do. Now for the input, we can concatenate ELMO embeddings with the original word embeddings from skipgram or glove, etc., as this. We have a model parameter lambda to scale the ELMO embedding, okay? So we change the input to these two kinds of models. And in the output, we could also, after we feed the ELMO embedding and original word embedding to the sequence encoder, we have the hidden, right? We further add a shortcut connection. We add ELMO embeddings also to these hidden vectors, okay? Before we do the output. All right. So then you realize in the previous slides, when I aggregate different layer hiddens, I have a weight S. When we integrate ELMO embeddings with glove embeddings, I have an S. I have a lambda. So this lambda and S can all be taken as parameters and trained. So this is how we can use ELMO. Okay, it turns out to be more sophisticated than just use the ELMO vectors as the input to replace glove. Of course you can do that, okay? But you can do something more complicated, sophisticated integration. And it turns out that when you use ELMO, okay, you sharply increase the performance of all NLP tasks compared to glove or skipgram, okay? Well, people are very excited. This RNLM turns out to be much more powerful than the n-gram LM, okay? But you say, can we use the same evaluation technique to calculate word similarity? Unfortunately, you can do that because every word doesn't have a fixed embedding. But you can still do word similarity in context. For example, you can have the play, okay, in different sentences. You can calculate their similarity. And you know words like play and bank and table, they have multiple meanings, right? And it turns out that words in a similar context will have closer vectors together. This is how you use contextualized embedding. Let's stop here. I still have a section on transfer learning, but we will discuss that next week.